Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to start a new modeling, design and analysis series covering silos. Of course, silos could be concrete, could be steel, could be all kinds of materials. My focus here is going to be on silos in general, and then I will talk about designing concrete and steel silos. So my reference for most of the topics I will discuss in this series is the ACI 313 2016 design specifications for concrete silos and stacking tubes for storing granular material. Now, please notice that the scope of this video series for the silos is going to be focused on silos that store granular material. Liquid silos are not covered today. They might be covered in the future. I think the specification for the ASI code for that is, I think, 375 or something. I don't remember that. I will have to look it up. With that being said, today's video is going to focus mainly on the silos loads and the silos configuration that you might be faced when you model a silo. Please notice that this ASI code works on concrete, but has some pointers with regard to steel silos. And finally, usually I use any standard to calculate loads, and then I basically leave it to the discretion of my dear viewer to use the design code or loading code he wants, because I'm trying my best to keep the series as code neutral as possible. However, well, concrete silos and storing granular materials, well, there is no, how can I phrase this? There is no code neutral method of explaining that, so I have to basically rely on the ASI code 313 2016 edition. All right, fantastic. So we need to start understanding the theory behind silos and what the different terms are. Now, of course, this is only an introduction video, and the reason behind this is that I want to ease for you the reading of the ASI 313 code. So, of course, I cannot, and I'm even not allowed to show you the entire code because it's licensed. So you have to get yourself your own copy. However, I can take outtakes of that code for educational purposes. So, okay, before I start explaining the outtakes, well, let's take a look on what actually a silo is. Now, there are two types of silos. There is the first type, which is a circular silo, and as the name suggests, it's a silo that has a cross-section made out of a circle going down. And the reason why we have silos is to store material. We are talking about granular material now here, of course. Now, usually such silos, because they store granular material, they do have an opening in the bottom. You could have a silo with an opening on the side, but this is a nightmare for granular material. Why? Because if you have an opening on the side, let's say that you have a silo that looks like this, and you have an opening on the side. Well, you fill the silo with your granular material to the brim. When you open this, the material will start flow. However, you will see that only this material gets extracted out of the silo and the rest remains static. It doesn't move, it doesn't change. And even over time, it might harden and will be very hard to clean. So for granular materials, usually we have our openings in the bottom of that silo. So this is, well, might work for liquid silos, but for granular silos, that is not even an option. So, okay. Since we have an opening below the silo, this means we need to funnel our material into this opening. Let me just draw here a circular funnel here, which means that we are going to funnel our material to basically flow from top to bottom like this to get out of the silo. Of course, there are different flows here. Each material has to flow differently, and they soon exit the silo. This is how material would move in a silo. And such movement patterns would change different pressures in this silo. So it's a little bit more technical and more tricky than you thought. It's not just liquid that is getting out of the silo, but it's granular material. So, okay, now there is a consequence here. Since your material is exiting from the bottom of the silo, then, well, you will have to keep your silo above the ground, which means you will have to provide a supporting structure. The supporting structure is usually made out of some elements, steel elements, concrete elements that surround the funnel, that surround the hopper, and basically is carried by columns, by 4 sides or 5 sides or whatever. Now, we'll be talking about the structure later for now, but for now I just want to tell you the basics of silos and all that kind of stuff. Well, let's go to the second part, or second possible type of silo. Second possible type of silos is, well, a rectangular silo like this. And, well, the rectangular silo has well-defined faces that in the end, once again, funnel into a small little funnel like this that exits the material. And the same thing is, you would have a supporting structure that supports this silo same way. All right, now, this exit, this funneling action, usually should be in the center of the silo because, well, it makes sense to have it in the center of the silo. Now, why is the pressure in the silo different than any liquid? The pressure in the silo is different than any liquid because you have so many things that interact when you open the opening at the bottom of the silo. Because when you open the silo, the materials will start flowing out, and this is not water. This is not a liquid. These materials have friction, internal friction angles, repose angles. They even friction with the walls of the silo, and sometimes you will see that some residue of the material will start accumulating on this edge. So it's a little bit more complicated than you would think, and luckily for us, the code does account for that. Now, before I start talking about this, there is a definition I need to get my head around it, which is called the Hopper height. The Hopper height is the height that we assume that the funneling action will start to take place. Now, it's usually easy to detect. It's basically the height when the silo starts sloping until the material eventually exits. This is HH, this is the Hopper height. Of course, there are multiple Hopper heights for a silo. Please notice that for most of our silos that you see here, you see concentric flow. This is a concentric flow silo. This is a concentric flow silo. This is a concentric flow silo. This is I can count it as concentric flow. This is debatable. This is an eccentric flow silo, which means we have two types of silos. We have concentric flow silos and eccentric flow silos. The difference between them being, well, concentric will cause flow waves or flow gradients to look like this, which are very well defined and determined. And eccentric silos would cause flow gradients that look like this, which means that it's a little bit different. I still am a fan of concentric silos because they will minimize the amount of static material I have. Static material is defined by the material that doesn't move. Imagine, which I explained just before, when you have a silo that has a horizontal opening here, for example here, then when you open this opening, the granular material will start flowing out. This would flow out easily. This will flow out easily. This will flow out harder. And you can see it's because of the tangent of the expected flow profile. If the tangent is too shallow, the friction angle will win this battle, if I want to coin this term, and the friction angle will overrule the flowing tendency of the material, which means that you have static material here. Static material means that this is material that will never move at all. So this is static material. This is basically dead material. And of course, the amount of static material increases the shallower your slope here is, the shallower your funnel action is. So it's something you need to take account for. Now, there are two types of flow, both of them having their own set of equations. There's something called mass flow and something called funnel flow. Mass flow, well, it's a little bit technical, but I want to term one coin. Funnel flow is basically what happens near the funnel, and mass flow is what should happen in the silo. The difference is in both mass flow and funnel flow, the unit weight and the friction angle do play a role, but I think that in mass flow, the dominant action is for the gravity and for the gamma, the unit weight of the material, whereas for the funnel flow, friction starts be taken into account because you have all this overlapping gradients that want to exit the silo. All right, so okay, fine. It seems that I'm coining some terms. I'm coining unit weight. I'm coining friction angle. I'm coining all kinds of stuff. So the question is, well, what gives? How can I know what the friction angle is? How can I know those information or data? And also, it seems that your ACI 313 is about concrete silos, but you said you wanted to talk about steel, right? Well, yes, because ACI 313 actually deals with both steel and concrete when talking about loads and materials. So for the load, at least, 313 will serve you right. Now to show you something as an outtake of that ACI code, the table in the ACI code, the commentary 6.3.1.3, talks about exemplary physical properties of granular materials. Now, please notice, this is good for initial assumptions, but if you have data from tests that contradict the data in the table, of course, the data of the test should take precedence. Now, there are all types of possible granular material. You see that there is absolutely no liquids. And well, for each of those materials, you have the density, which is the gamma, in kilograms per meter cube. You have the angle of internal friction, and you have the angle of, there are two angles of internal frictions actually, and I will tell you the difference later when I start calculating. The coefficient of friction is, well, look, the difference between the internal angle of friction and the coefficient of friction is as follows. This is between the grains of the material itself. This is between the material and other kinds of structures. Alright, so why should I care? Well, you should care because when materials want to flow in a silo like this, when materials want to flow in a silo, they actually rub against the walls of that silo, creating wall loads. So let me try to explain to you in a nutshell what those loads are, but there's more equations actually, so it's not that easy to be just summarized into one sentence. But let me just in a nutshell try to explain to you the two types of loads you have and the reason why you have them. Well, the first thing is when you load your silo, it's loaded now with an angle of repose, and then you empty your silo, so you open this opening. If you open this opening, then the silo will start to empty, which means your granular material will start following the paths to the exit of that silo. Of course, we're assuming that emptying is happening at a normal rate, because otherwise dynamic effects would be taken into account that are actually approximated in this code, but then the approximation will fail. So if you empty your silo, then, well, two things happen. The first thing that happens is, well, there is friction. The walls feel friction. There is internal friction between the wall and the granular material when it tries to move, and that's the reason why you need the coefficient of friction against concrete and against steel. With a nice little note that, well, steel seems to be between 40 and 70 or 60% of that of concrete. Makes sense because steel is much smoother than concrete. Well, so the walls feel something dragging it along with it because, well, the granular material wants to go down. So this is called wall loads, and this is something you have to take it into account. Now, why is this dangerous? Because there are two types of wall loads. The first one is, well, the vertical load, and the other one is the horizontal load. The horizontal load on the wall is due to, well, the lateral pressure of the granular material. You know this from your foundation engineering. There is active pressure, passive pressure, all kinds of pressures. So, wall feels two things: horizontal loads and vertical loads. Truth to be said, the horizontal loads actually control the design of the horizontal steel, because you are going to design for 1 meter strip and check out how much steel you need. If it's a perfectly circular silo, then the only thing you would have is tension forces. If it's a rectangular silo, then you would have tension forces and bending moment, but this is something I will show you later in Robot in the next video. The wall loads seem to be less harmful, somebody would think, because they control, well, they apply compression on the silo, so they shouldn't be dangerous. Well, no. Wall loads are actually dangerous and control silos if they are really high. Because if silos are really high, this means that it's easy to buckle the wall of the silo, which means those wall loads, friction loads, if the silo is high, could eventually buckle your silo. So, well, this is just a little thing I wanted to tell you. Usually, it's just a check and doesn't control anything, but in some rare cases, well, it controls. This is about wall loads. What about hopper loads or funnel loads? Well, this is a little bit different because you see now you have here two types of forces. The first force is, once again, friction and stuff. And the second force is, well, the gravity force, the gravity load of the granular material above the funnel. And the problem is, it's not easy because there are two cases for this gravity load. The first case is when there is absolutely no flow. In that case, you have static conditions. If you have a silo with no flow, then, well, you could say, well, the gravity load here is basically the pressure from the soil, which should be gamma multiplied by h. This is, well, partially true, but not really true. Why partially true? Because the weight of the soil is not only carried by gamma h, but it's also carried by the wall friction. You will see some strange terms in the equation for loads that have to be related to friction, exponentials, all kinds of nice stuff. You will even see that the equation has to do with the amount of area of the silo versus the perimeter of the silo, because the area of the silo will actually cause the pressure, or is part of the load causing the pressure, because gamma multiplied by A multiplied by H would be a full force. But still, The perimeter plays also a role because, well, the perimeter is related to the friction, which try to alleviate the pressure on the hopper. Well, this is in static conditions, but imagine the dynamic conditions now. When you have dynamic conditions and the silo granules want to exit, then you have all kinds of problems because first, you are now in the dynamic regime. Second, the funnel tries to change the direction of the flow, causing force on this wall, and this force needs to be accounted for. And of course, you can imagine an extreme case, where this is not well attached to a silo. In an extreme case scenario, this will fall down. You open the granular floor and then close it suddenly, you will basically cause this to fall off because it's not held well. So it's important, and you need to take this into account. All right, fantastic. So going back to our table, you see that for each type of material, there is density, friction angles, coefficients provided in the ASI 313 code. Those are, once again, I repeat, those are predictive values that can be used in the design. But if you have laboratory values that even contradict those values, then you should use your laboratory values. But I think that most of the values here are well established, so I think you can use them with confidence. All right, so about the loads. Now I will give another video about the loads, and maybe it's video 3, because the second video will be the start of the modeling. But just to give you a small idea, there are multiple loads that you need to take account when you design silos. The first thing is the pressure due to initial filling, meaning, well, the silo is empty, and now you want to fill it. When you fill the silo, after you finish filling, basically, you have loads on the silo, and those loads change with the depth of the silo, meaning if you have a silo like this, if you talk about fluids now, imagine you talk about fluids now. Well, fluid is easy because the pressure on the fluid looks kind of like this, with 0 on top, and of course gamma multiplied by h on the bottom. It's perfectly fine for fluids to be like this because there is no internal friction, there is no friction angles, nothing. Well, here it's totally different. Here you see, first of all, Q is gamma, but I see no H because usually it's gamma multiplied by H, right? Like, where is my H? What gives? Well, actually, it's gamma multiplied by this factor, where you have your H called Y here. But why this complicated equation? Well, I told you before that you have friction and you have load, and it must be taken into account. You can see mu, which is the friction coefficient. You can see K, which might be the horizontal pressure. It's a very long story, by the way, and I will have to take you once again step by step later in video 3 to dissect each and every one of those. I might even draw the relationship in Excel to show you just a feeling of how the pressure if the silos looks like. But for now, I don't want to information overload you. This is the first video, so my goal in the first video is to give a small introduction to the case and provide you with the recommended reading material that you could read to prepare for the next videos. All right, so of course you have vertical pressures. This is the vertical pressure, and you have horizontal pressures. The horizontal pressure is easy. The horizontal pressure is the vertical. Now this is actually not that hard. The horizontal pressure is the vertical pressure multiplied by the K factor from soil mechanics, which is 1 minus sine theta. Please notice that you need the horizontal pressure because you need to design the walls of the silo. In fluid mechanics, it's also gamma multiplied by H because both the vertical and the horizontal pressures in fluid are the same. But in soil, there is a factor called K, and you use it to find it. Next, there is the vertical load of friction per unit length of the wall perimeter at depth y. So what the equation here is giving you the friction force per unit length of the wall perimeter. So if the wall perimeter is, for example, let's say the wall perimeter is 10 meters, then the total friction force that this wall feels at that position, y, is actually 10 multiplied by this v, because this v gives you the friction force per unit length. So if you have a perimeter of 10 meters, then you have to multiply your v by 10 to get the full vertical load. Now notice that the friction load here changes with height. This makes sense because think about it. If you have a surface that is rough and you have a box on that surface. Well, the amount of friction force that you get when you try to move the box is F, and of course it's F kinematic or F statics, let's say F static for now, which equals mu, the friction coefficient, multiplied by N. And what is N? N is the vertical reaction you get from the surfaces, which means the more you push on the surface and cause a greater reaction, the harder it becomes to move something. And this is basically a clamping action. This also takes place in the silo because think about it. What is the force that pushes perpendicular to the surface and causes a reaction from the surface? This force is basically the horizontal force, P. And this P force is related ultimately to the vertical pressure, Q. So it stands to reason that the friction force per unit length here must have to do something with the height at which you are, or ultimately Q. So we'll take a look, and lo and behold, it's related to Q and your height and your gamma, which is, well, something I was expecting. Of course, we will take a deeper dive in the loads video, which is going to be video number 3. Those are basically the pressures at initial filling. And okay, fine. Now, please notice that there is an assumption here when you do all this kind of pressure. All the things you see in these equations are basically derived from this assumption that I will have to talk about later when I take a deep dive in my loads video. But for now, just keep this in mind that it's assumed that this is the shape of your silo when you fill it. Because you cannot fill it to the brim, because it's just a silo, it's a closed silo. You keep filling it until, well, the soil or the granular material that's inside reaches the surface. Of course, there will be pockets of air because, well, the granular material has an angle of repose, because if you pile up a bunch of sand, it will not just get horizontal, it will pile up in a small cylindrical cone. So this assumption was also taken into account in the code. All right, so we talked about mass flow, we talked about funnel flow, eccentric and concentric. We talked about this. The last option here is to talk about the loads on the hopper. And please notice that there are two basically actions you need to take into account. The first thing is the hopper loads under a mass flow. If the hopper is very well inclined, which means that you will have a mass flow, not a funnel flow, and the hopper under a funnel flow. Of course, how do you know if you are under mass flow or hopper flow conditions? Well, the code does show you this. It tells you that, well, if you have a certain hopper configuration with an angle of inclination and the friction of the hopper and the granular material, then you have a chart that suggests to you what kind of flow you have, a mass flow or a funnel flow. And depending on this classification, you can actually start designing. So, okay, well, the initial, once again for hopper, the initial filling pressure below the top of the hopper, well, is basically QV, which is Q0 multiplied by gamma multiplied by H of the hopper. And it's basically a very simple equation here. Q0 being the vertical pressure at the hopper, calculated from equation 6.3.2.1. Now, what was 6.3.2.1? It was this equation. The one where you have all those factors inside it. So Q0 is basically, according to this equation, Q0 is the pressure at the hopper height, below the top of the hopper. Now, it continues by telling you, well, you add to this gamma multiplied by H, which is, well, expected. It continues by telling you that, well, there is a pressure normal to the hopper surface. Why? Because remember I told you that the hopper actually is funneling the material into the exit of the hopper, and according to fluid dynamics, to aerodynamics, to all kinds of dynamics, if you change a vector from going down to going into an incline, you need a force to cause this change, and this force is being exerted from the soil onto the hopper, and this is the normal force on the hopper. Of course, there is an equation that tries to show you this. I will go back to it for more detail later, but you can see that it has to do with both tan theta of the soil and other thetas of the effect. The result of, so basically it has to do with a lot of friction angles here that I will talk about later. And notice that this is a force normal to the surface of the hopper. you can actually calculate the uh, initial friction force per unit area, which could be a stress, and it's also given. You see, it actually tells you all kind of the equations you need. Now, please notice that you have an initial condition, and the word initial means when you fill the silo, but do not start emptying material. Then, when you empty material, you have two possible cases. You have funnel flow, and you have mass flow. And both of those flows are explained in those equations that you see here, which I will basically dissect when I get to my load video. But for now, I just want to introduce you that, hey, there are equations, and you can see that it's all kind of interesting. And it depends, of course, on the cone type. If you have a circular cone, which is usually used for a circular silo, if you have a plane flow hopper, this is usually used for a rectangular silo. Then, of course, both of them have different equations. If I want to do everything in one video, of course, it will be 3 hours long. I'm targeting my first video usually to be an introductory video and to be 20 minutes long. This is a quick and short introduction to the world of silos. And, of course, I recommend you to read the ASI Code 313 2016 edition. So basically, get it, buy it. It's available online. You can check it out. And read it. It's recommended reading for you because I will be using it not next video but the video after it when I start calculating the loads. The purpose of this video is to introduce you to the world of silos, tell you the different terminologies that you have to keep an eye on and what they generally mean. I didn't go into painstaking detail yet because it's an introduction video. So also I want to apologize of what seems to be a lower quality video this time because I'm on a conference, so I'm out of my home base. I don't have my usual equipment with me. Also, I think in one of those moments in the video there might be external noise. Well, as a matter of fact, I am in the hotel lobby. But well, I didn't want to miss uploading a video this week, so I tried my best. All right. So, what are the next videos to be expected? The next video is going to be a first try at modeling the silo without loads, and talking about all the different aspects of modeling those silos. Then there will be a load calculation video and applying those loads, and then there will be a design video. I will try to model and design both concrete and steel silos, and I hope that, well, you would find those videos beneficial. Anyway, finally, and of course, as usual, I hope that those videos are beneficial to you. And if they are beneficial, well, why not like, share, subscribe, and comment? Especially subscribing, and because it helps me increase the reach of my channel. So suggest this channel, if you like it, to your colleagues. Well, as per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.